Hello friends, today we will continue uh, modeling of pipes. Yesterday we left here, correct no? I think we have modeled up to this portion. Up to here we have modeled, okay. So after that we need to continue. The line is going towards downwards. So before that I forgot to tell you one thing because after I observed that there is a major mistake. See, at this well, they given there is a code break from this flange, from this valve onwards. Code has been changed to 31.8, and yesterday I didn't see, and I used 31.3 itself. So today we'll see how to change that one. Okay. So that is up to this after this one. So up to this flange it is 31.3. So if you select, if you go to the right one, you select piping codes. So we'll see all are in 31.3, but as per isometric drawing, it is 31.8. You see, and material also it is carbon steel HDP lined. So you need to change the material accordingly. Okay, and also the code it is 31.8. 31.8 is for the gas pipeline. It is cross country pipeline for gas services. So now what we are going to do, you have to select this node number. You select this node number and go double click allowable stress, and then here in the code you need to change it to 31.8. Okay, so in 31.8 automatically this will appear the allowable stress. In this case it is not allowable stress. If you go to help, I will come to know what is T1 and what is T9. Okay. So in 31.8 is temperature deaerating factor. That you have to refer 31.8. You will get what is that in that as per the table 841.116. Okay. So up to this, up to node number 2030, it is 31.3 that belongs to piping, and after that it is pipeline. So here what we need to change, we have changed the code. Okay. And then here it is restraint and unrestrained. You see, allowable stress indicator it is given as CAESAR determines, and restraint pipeline, unrestrained pipeline. A restraint pipeline for the buried portion and unrestrained pipeline for the above ground portion. See, just leave it. If it is above ground, you just leave CAESAR determines, or you can give unrestrained pipeline. Any one you can give, not an issue. Okay. So this is 31.8, and your material is, go to the next sheet, you will get the material. You see, material is given 8-inch CS ISO 3183 grade L290 PSL-2. So in the bracket they given us API file grade X42. So you select this material. It is available in the CAESAR. API, you just type API here in the material. You select here and type API file grade X42. You see here it's there. If you know the the material number, directly you can enter 330. You see, if you know the number 330 means it will come API file grade X42. Okay, and what is the thickness? WT weight. Okay, wall thickness. Wall thickness is 4.8 mm. So you need to change here as 4.8 mm, because the wall thickness calculation is different for 31.3 and for 31.8. Okay, That once I get time, I will explain you how to calculate pipe wall thickness for 31.3. Okay. And other things remain same, I think so. Or if any line number change in the line number, then you need to check the parameters. So I think everything is okay. Okay. So only thing, this code has been changed, that we have updated now. So now if you select this code here, piping code, see up to here is 31.3, and after that it is 31.8. Till here it is 31.8. And for the PSV lines, PSV belongs to piping. So what we need to do, we need to update once again, because from here onwards only 31.8. So your PSV line is coming before only. So here it is 31.3. So your PSV is here only. So what we need to do, go to the last node number, this node number, go to the next element. So this next element, that is this portion. You see, it's highlighted in yellow color. So this is this one, and again you have to select, double click allowable stress, and change the material as, change the code as 31.3. Okay, so if you select 31.3, automatically this will change, and here you need to change it to 1. The material is 106. No, go to the PSV inlet line. So what is your material? A106 grade B 3-inch schedule 40. So you just type 106 here. The material has been changed, and here 3-inch schedule 40. Okay. So now if you see, again you select this code. Now it is 31.3. So the entire portion has been changed. And here only 31.8. So you can change, you can check the material also. If you select the material, here it is A516, A106 grade B, and here it is API file, just expand this one, API file grade X42, and one more material is there, that is B423. You say yes, for the inlet line up to here it is B423. Okay. So like this, if any spec break or any code break is there, means you have to define like this only. You have to check properly. Okay. And also regarding the reducer, today I seen one person model in a different way. For example, so we have model from inlet to outlet, correct, no? So how we have model? So we have model like this. So for this, what we have applied yesterday, from small bore to big bore, so we have defined, no need to change at this node number. After this node number only, you need to change the diameter. That person, what he did, he just entered here, and here he has given 2 inch. So it is in the reverse way. It is not correct way. Okay. So up to here you have to model as the previous node number. That is 2 inch means 2 inch only. Okay. And in the after selecting the reducer, you have to change this one to 3 inch. Okay. And 80 schedule. Okay, so you have to be very careful in the modeling point. If you do any mistake, then your output will be changed, and analysis also will be wrong. Okay. Okay, we will continue from here. Okay, so this is our last node number. And I told no material. Material you have to use only the pipe material. Okay, don't use any flange material or any teeth fitting materials and all. Don't change anything. Only the pipe material you have to use, even for the flanges, fittings, or any inline items. Okay. So this is a material. And then go to this node number. I'll see for the next node number, and here it is no continue. If you give continue also, it will go to the next node number. Okay. So the line is continuing in the vertical direction. Okay. Outlet and our sheet is, yeah, here. This is the outlet, and till here we have model. Okay. So after this, it is 172 and one T is there, minus 172. Okay, so it is getting continued, and we have copied this portion, correct? No? I mean, we have modeled this, and we have copied and we have pasted here. Okay, so what we need to do, we need to check properly the other thing, the line number and all, whether it is correct or not. You need to check properly, because the same line number only it may be repeated. Okay, so you need to check the line number and update accordingly. Okay, understood? No? Okay, so next is just select here. Scroll, I am just scrolling. Okay, scroll in and scroll out. Up to 172 we have model. After this, see, again on spool user, that is on sheet 12. So we don't know this spool. We will go to sheet 15. This is sheet 15. So this elevation, there are some spool. So they are not given the dimension. So if this is T means we need to check the T dimension. What is the line size? 3 inch by 2 inch. So in the pipe data pro, go to fittings, butt welded fittings, select reducing T 3 by 2, 3 inch by 2 inch. So what is your dimension? Your T is in 86. So your T is in different direction, correct? No? So this is this 76 is this is 76. This direction is 76, and this direction and this direction it is 86. Okay, so your vertical dimension is minus 86. So you have to give minus 86. But already T has been defined. Yeah, okay, that is one more T. So here you need to select T, welding T, and then minus 86. So if they are not provided the dimensions, you have to check the fitting code, fitting standards. So for butt welded fitting, it is ASME B 16.9. If you refer 16.9, you will get all the butt welded fitting details. Okay. So it is continuing in the next line, next sheet. So this code is 31.3 only. There is no change. And now you see it is 780. So it is going minus 780. So you see after this, this is finished ground level. Finished grade level is 100. So this is your ground level. This is your ground level. So below this, it is buried. You see, it has, I mean, the isometric, the line has been shown in dotted lines. That means it is going in the underground. That is buried line. This portion, from this portion onwards, the line is buried. It is filled with soil. Okay. So I will tell you how to model the buried lines. Just you continue the model. Then once you complete this model, then we need to change this model into buried model and then do the analysis. Okay. So up to 780 wave model, this node number you have to remember, that is 4790. Okay. And then after that 1323, it is going vertically. The model remains same only. Modeling procedure remains same only. Only thing, after completing this model, we need to convert this model into buried. We need to apply the soil properties, then convert the model into buried. Then you will get the soil stiffness on the pipe. Then run the analysis. Okay. It is 1323 and the line is going in which direction? Okay. For our reference, just I copied this. So the line is going in minus z direction. You see which direction it is going? It is in this direction. That is minus z. Okay. That is how much it is? It is 2500. 2500. 1 minute. You see the slope it has given. Here you see slope has been given. And this line is sloped line. 1:200 towards this side. I mean, line is like this. Okay, and it is going in this direction. So your slope is like this one. Actually, your line should be like this. Sorry, wrongly drawn. Your line is in this direction. Okay. Like this. So this is your actual line. This is your actual line. And the line is like this. After that, the line is taking a turn and it is dropping. This is the slope. How much the slope given? 1:200. You see, for slope line, elevation will be mentioned as WP. WP means working point elevation. Okay. So there will be a difference in elevation. You see how much is difference? 98.677 minus 98.664. So there is 13 mm difference is there. Okay. So how to calculate the elevation difference? Our overall length is 2500 from here to here. 2500 divided by our slope percentage ratio 1:200 divided by 200. You will get the dimension of the slope. Okay, vertically how much it is? 12.5 mm. But from the elevation, how much we got? 13 mm. So it is approximately 13 mm. So they rounded off and they given 13 mm. Okay. So how to model the slope line? I will show you how to model the slope line. So here bend is there. Go to the next node. And it is going in minus z direction. Correct? No, it is going in minus z direction. You have to give that dimension minus 2500. Like what we have given, no, for the offset lines. The same procedure only we are going to follow. Okay. So any double direction, two directions the pipe is moving means we have to give two directions in the particular node. That's it. Okay. So now Your slope is in y direction only, vertical only. No, your slope is in vertical, like this. Okay. So that means you have to give your slope as minus 30. So you see, since this is very, very less, you cannot see. I will show you this one in a different view, left view. You see, since the slope is very less, you cannot identify. You see, if the slope is very, 130 mm, then you can see pipe is towards downwards. Okay, like this only your pipe is going there. So since the slope is very less, 13 mm only, it's not showing that much difference. Okay, so your model, we are modeling from here. From this elbow we are modeled. Okay, suppose if you are modeling from here, then you have to give that 13 mm in the positive direction. Okay, because your 13 mm is this. So we have modeled this one, and if you are coming this way, then it should be in positive direction. Now we have gone in a different way. Understood, no? Okay, like this. Now we have gone like this. So now we have modeled from here. We are gone like this from here, vertical, and the line, it should have traveled like this, but there is a 13 mm difference. This is the vertical 13 mm difference. Okay. So I assume the skew like this. So how we will model like this means it is in the negative direction. Okay, your line should have traveled like this, but it is traveled like this. Okay, this is your actual model. That means your line is skewed in vertical direction. That is slope. Okay, it is in vertical negative direction. That's why I have given us minus 30. Okay, so here bend is a double click and go to the next node, Alt C, and then you see again slope is there, and what is the dimension? 2, 9, 5 and 3, 29 meters, 29.5 meters. So since the slope is same, what we are going to do, we are going to use this one. You see, double click here. Okay, since you see, if any slope or any skewed line, you will have the cosine value, because since in y direction only we have defined the cosine. I mean, that's why it is showing minus 0.005. It is in negative direction. So since the slope is same, we are going to retain the same slope. So we will enter 29,513. What is it? 29,513. Okay. So if you select here, you see minus 156 it has been given. But in which direction? You have to check the direction. So this is in Z direction, but it should have been in which direction? Minus X direction. Till here it has traveled in minus Z, and after that is taking a turn and it is going in minus X direction. Correct? No, it is going towards this. So minus Z direction. So you enter this value in minus X direction. I just copied. You see, automatically it got changed. Okay, and you have the vertical dimension of 153. So we need to check. You check the subtract the elevation. 98664 minus this elevation. You see up to this point only we are going to model. It is 98516. 9 sorry 98664 minus 98516. So approximately 148 mm. So what we got? 153. So you change this one to 148. So whatever is given in the isometric we will use. Okay. So you can check 29513 divided by 200. So 147.5. That is our slope dimension. So we are using 148. They rounded it off, and they use minus 148. Okay. Since you have this much length, what we need to do, just give higher node numbers, because 29 meters. For example, every 6 meters support is required, or every 4 meters supports are required, means just change this one to 4890 or 4019. Okay, just for the safer side. If you want to break, or if you want to insert something, or like that, means then you have to model accordingly. You have to increase the node number. No issue if you are not going to break any element also, no issue if it's on the higher side. Okay. So next, up to here we have model. Again there is a skew. So it has been, it is moving. It should have gone in minus x direction and plus z. It is going in minus x and plus z. So it is 45 degrees. So since you see 45 degree means both dimensions are same only. So 1787 minus x, in the minus x direction 1787, and in the z direction plus z 1787. So go to the next element. Minus x is minus 1787 and plus z is 1787. Let's see, it has been changed. Okay, so we have modeled up to here, and again we need to check. Yeah, the here also slope is there. So what is the slope dimension? 98516 minus 98503. Sorry, 98516 minus 98503. 13 mm differences. So we need to see whether we are not given any. So in the vertical dimension, you have to give minus 13 mm. Okay. And again, you see, it is going in minus x direction. Minus x means 16875. Go to the next element. Minus 16875. So if this, like I have to define bend here. So like this, bigger dimensions are there, means better use more node numbers. 4930, just I am giving 5000. Okay. And here slope is what is the elevation difference? 98503 minus 98419. 84 mm. So 84 mm difference is minus 84. You have to give minus 84. Okay. So up to here we have model. So up to here we have model, and again there is a skew. It is 45 degree only. It is going in minus z and minus x. Since we are modeling from here, I am going like this. Okay. Minus z minus x. That is both are 7700. Go to the, you have to define the bend. So it is minus 7,700 is minus Z. Sorry, 7,700. And in minus X, same 7,700 only. Okay, it is correct only, no? So overall dimension is 10,890. Okay, and you have to provide the slope also for this one. 98365 minus 98419. So minus 54 mm dimension. So here what we have to give, minus 54 here. Okay, and you have to enter the bend here. So up to here we model, and after that 6298 is there. 6298 minus 6298. Sorry, it is in going in minus X direction. It is going in minus X direction. Correct? No, it is in minus X direction. So after that, you can see some reducer is there. Reducer is eccentric reducer. RED eccentric reducer. You see, BF means flat side bottom. This is a flat side. Correct? No. So this is a flat side. So flat side at the bottom. Okay. So we need to see what is the overall dimension of the reducer. Go to the next sheet. You see, the dimension is reducer dimension. It is clearly given as 102. Or if you want to check in the pipelet approval, go to the menu, fittings, butt-welded fittings. So already it is there. And go to the butt-welded eccentric reducer. That is ours is 3 by 2. You see. Sorry, what is our this one? It is 3 by 4. Sorry, 3 by 4. 4 by 3. Okay. You say the dimension is 102. Overall dimension is 102. Go to the next element. Alt C. Minus 102. Sorry, minus 102. And it is like, and your offset is 13 mm. So it is flat side bottom. Here, if it is like this, flat side bottom, it is 12.7 mm it is given. So here is 13 mm they have provided. So we can use 13 mm. That means you have modeled here. I mean, so we are doing the modeling from here. Okay. So that's why up to here you modeled. And after that, you see the dimension differences in positive X, positive Y direction. It's in vertical. Okay, vertical positive Y direction. So that's why we need to give here as 13 mm in a positive direction. Okay. And you see, you have to select a reducer and enter the diameter, next diameter. That means it is not reducer from smaller size to higher size. So we will call it as expander. Okay. So we will call this one expander, and the next size is 4 inch. So what is the 4 inch schedule? 40 schedule. Okay. Then 4 inch 40 schedule. You see, this is flat side bottom. I will show you. We will model the next one. I will show you the view. Then 400 mm is there. Okay. After this 400 mm. Go to the next element. It is in minus X direction, 400 mm. Okay. So you can see, because you see if you have provided here 4 inch dia, automatically the next node number will be changed to that 4 inch only. Okay. So don't give wrong this one only. And if you go to some other view, left side view like that, or right side view, front view, we'll see. I want to show you. Yes, yeah, that's the front view. You can see the difference. No, this pipe and this pipe, they are matched. In order to match the bottom of pipe for AC supporting, so bottom I mean they have to match the bottom of pipe. Okay. So for that, what they given extended reducer. You see, all are at the same location. If they use constant gradation, what happen? If they use constant reducer, your reducer will be like that, and this pipe will have in a different dimension. I mean elevation. This pipe will be in the different elevation. So that's why in order to match the bottom of pipe, they used here eccentric reducer. Okay. So if you have any doubts, please discuss with me. I will share my phone number and mobile number. Sorry, this one mail ID. You can discuss, or you can send mail also. I will reply to you. Okay, so here, so after this, it's entering into some, I mean, puddle flange, some wall is there. So inside the wall, it is moving. Up to 400 we have modeled, and then 350 is the dimension and 980. So we will stop here. Okay. Go to the next one. Minus 350. 350 and 980 is the minus 980. Generally at the puddle flange is the flanges that is used for any pipe. It is penetrating a wall. So they will use the puddle flange. So what we need to do, we need to anchor at this location and provide the load to the civil team to design the puddle flange. Okay. So we need to transfer the load. So what we need to just, I will anchor here at 350. Just anchor here. Just anchor A and C. Type A, you will get the anchor. Okay, we will stop it here itself, not an issue. Okay. So what happened? You see, up to here it has been in daughter lines. We'll see. Go to the front sheet. Yeah, up to here it is in dotted. I mean that up to here it is buried. So after that, after this reducer, it is above ground. So this and all, I mean, 1 minute I will open. Yeah. So from here to here, it is buried. Up to what node number? It is 5040. You have to check 47902 to 5050. You have to remember this one. Okay. Okay. So now we have completed the entire modeling. So now we have completed the entire isometric drawings. So at the end, we are at the end. So once you complete the model, you need to check the inputs. You have to check all the design parameters, insulation density like this, whether it is okay or not, and fluid density, pipe density, corrosion allowance, pressure. So whether you have defined the pressure in a correct manner, you see, pressure, hydro pressure, design pressure and hydro pressure, and wind or wave, and then seismic loads, melt tolerance, that is common only, and thickness is very important. You need to cross check 1 or 2 times. Okay, this is for a self check. Once you complete the model and after analysis, your lead engineer will check. Okay, and diameter also important to define correct diameter, and insulation thickness if anything is there. Then pipe codes. So pipe codes we did one mistake and we have corrected today. And then material. So material also very important. Okay, so like this, we need to check all the inputs. Not only this one, you need to check everything. Okay, and coordinates. If any coordinates is there, you can give coordinates here. So here I think the first node, any coordinates, elevation they give. Now what we will give? We will provide the elevation here instead of all the three coordinates. What we will do at the node number 20, first node number, we will define the elevation 101.30, 101.3303. Let's select OK. Okay. So we have defined the coordinates there. Now you can check at the last element. So where we have stopped here, at least here. Okay. Before the reducer, we will check. At the reducer point, how to check the coordinates. The same measure also you can use. Distances, distance. And in this, origin to 2 nodes. Origin means from 20, that is the start point, okay, to particular 2 node, whatever we have selected, 5040. You see, origin is 20 and your current selected node is 5040. So you will get the coordinates, you see. Some coordinates x and z we have not defined, but it is considered as 0 at node number 20. After that, it has calculated and it has given some coordinates value. But we know the y dimension. It is 3021 minus 3021. But what is ours? 98.334. So what we have defined, but something wrong. We did something wrong. Okay. What is the first node number? Elevation. 101.33. Correct only. 101.33. Here we need to check the coordinates. Here what is the elevation? They have not mentioned the elevation. Yeah, from here onwards they have mentioned the elevation. 100.952. I think in the isometric drawing some mistake is there. I will show you how to measure the, like this only you need to check the coordinates. Okay. So if 3021 means something wrong is there, we will see in the next inputs. In the next isometric drawings I will show you how to enter the coordinates and how to check our model. Everything I will show you in the next isometric drawings. Okay. So like this only we need to model the above ground piping. Now we will see how to apply the reaction force. For any PSV, you have to apply the reaction force. Generally reaction forces will be provided in your PSV data sheet. Reaction force is nothing but during pop-up condition, what happens means, if your pressure exceeds, if the design pressure exceeds the system pressure, so safety valve will have some set of pressure. That is safety valve set pressure. So what happens means here this will pop up, this will open up. This PSV will open up and pressure will be released here, and the fluid will move here and it will be collected to the pit. So in this case it is collected to the pit. So this may be considered as a closed system. Sometimes there are two systems in PSV. One is open system. Sometimes the pipe is going like this and it may went to atmosphere like this. Okay, so this is an open system. Like this means it is open system. So for flare header and all, if you see flare header you will have like this. So your PSVs will be connected in a different like this. Maybe in the 45-degree only it will be connected on the flare header and all. Okay. So on the flare header you will have different phenomena. We have to use lateral load for the flare header. I will show you one flare header line. Just a minute. You see, what I did, file, recent piping files. If you opened any file, so you can view like this. If you know the file name, then you can easily open. So this is some flare line. This header is flare header. This big line is there, no? This loop. And all this is a flare header. And PSVs will be connected like this. You see, PSV. Sorry. PSVs will be connected like this. So all flare header, you will have a lateral load connection only. So this is a PSV outlet. So inlet may be coming from some other equipment. This is the inlet. You see, this is some equipment. From there, line is traveling, and this is your PSV inlet. This is your inlet. This is your inlet, and this is your outlet. Okay. So you see the forces has been defined at this junction. Okay. So this is called as closed system because the fluid is traveling, again it is going to some other header, some other flare header. So the flare header, after this flare header, line will be traveling to the knockout drum, and after knockout drum it has been traveled to the flare stack and it will be vented out. Okay. So this is closed system because since it is very close, it is connected to some other header, it is closed system. And if the line is going like this and the line is atmosphere, it is moving to atmosphere. Okay, so in the atmosphere means the 45-degree only they will use. Okay, 45-degree elbow only. Okay, so this is a open system and this is a closed system. For any system, you have to define the reaction force. I will show you how to calculate the reaction force. Okay. And how to apply the force. First, generally it will be provided, the reaction force will be provided in our data sheet. For example, this is your PSV data sheet. You see, the PSV dimension has been given A and B. This dimension you have to refer here. A is 4.13 and B is 4.5. Yesterday, no, they have not provided clearly in the data sheet. In this data sheet, they clearly. So here, reaction force. If you see reaction force it is given here also. 1 minute, I will close this and again open. Okay, you see, this is a PSV data sheet and reaction force. Yeah. So reaction force it is given as 13.9 Newton. That depends on the PSV. The reaction force has been calculated based on the formula. If you see, they would have given as per AP 520 and as per AP 526, where orifice area will be selected. So you see, this is a formula they have calculated. This is for VL, and for the reaction forces we have the formula. I will show you the formula for the reaction forces. Okay, so like this, based on the vendor data, you have to calculate the reaction force. For example, here, if it is a closed system, you need to apply the force in vertical direction. And for the open system, in vertical direction as well as in the horizontal direction. But we will follow this one only for the pop-up condition. Okay, generally it will pop up. So what we will do, we are giving forces in upward direction and also towards the opposite to the flow. So your flow will be like this your flow, and we are giving forces in the opposite direction. You need to enter the values here. What is it? Orifice area, calculated orifice area, and mainly you need to enter the whatever highlighted in yellow color. Those things you need to enter. Then you will get the value of forces here. What is F1, F2, F3, and F4. Okay. So if any of the value they are not provided, you don't have this spreadsheet or you don't have the data sheet of PSVs like this. If they are not provided only, you can calculate. There is a thumb rule and there is a engineering, based on the engineering experience. One more formula is there that you can use. That is nothing but 2 into safety valve set pressure into orifice area. Okay. So you will get the safety valve set pressure from the PNAD, and 2 is your dynamic load factor DLF, and A is the orifice area. So from where you will get the A orifice area, you will get it from API 526. To go to API 526, this is API 526. So we need to check the orifice. In the PNAD they used to mention which orifice means. And the isometric also they used to mention. For example, if you see this isometric drawing, 1.5 F2. This F is your orifice designation. Okay, 1.2, 1.5 is your inlet size and 2 is your PSV outlet size. So F is your orifice designation. And in AFA 526 you can find different orifice. Okay, E, F, A, B, C, D like that. So here you have F orifice. For the F orifice, yours is 1.5 F2. And what is our rating? Rating is 150 by 300 by 150. Inlet is 300 and outlet is 150. So your inlet is 300 and outlet is 150. Okay. For F means you have only one area, that is 0.307 inch square. Okay. So that value we will enter here. You know, 2 is the dynamic load factor, dynamic amplification factor, and P is your safety valve set pressure. Okay, you see, P is safety valve set pressure, and orifice A is orifice area. That from AP 526 you will get the value. Okay. So you have to enter the values correctly, 0.503. Okay. Then you will get the reaction force in pounds. So if you want to change a unit, you can change a unit accordingly. If we need Newton means you need to give Newton value. You have to correct. You have to give in a correct manner. 1 minute. I will open our file. So we will apply load here. So we will see what is our designation is. It's in P maybe. So 0.503. What we need to see. 1 minute. 1.52 inch, and this is your set pressure 4430 kilopascal is given as 4430 kilopascal. So you need to convert this one. For example, 4430, this is kilopascal, and variation 0.503. So you need to change this one. You need to convert this value. So using converter you can give. So in the online converter we'll check. Okay. How much? 0.503, no? Yeah, F is 0.307, sorry. So F is 0.307 inch square. So you need to convert in mm square or something, or meter square, something like that. Inch square to mm square, we'll see. 0.503. 645 is your mm square. Okay. What we'll do is just add one more column here. Sorry, we'll add here. We'll convert this one. 645. This is 645 mm square. Instead of inch square, mm square, we'll write it here. A is in mm square. And P is in kilopascal. So we need to change into Newton per mm square. We'll see. Then only we'll get Newton value, no? So kilopascal to Newton per mm square. What is our value is 4430. From the ISO you will get it, or from the PNAD you can get this value 4430. Kilopascal 4430. That is 4.43. So ours is 4.43. So ours is 1.5 F 2 inches. Okay. So now you got it. No, we need to change this one. So we have changed from kilopascal to Newton per mm square, and this one, because we need value, we need reaction force in Newton. That's why we have changed the value units based on our requirement. Okay. So now this has been calculated. You see, D5. This is 5. No. D5 into D4. D5. This is D5 into D4 into D3. So we'll get 5714 is our reaction force. So we will consider one force. Since we have modeled like this from the dimension here to here, so you select at this junction. You need to apply the force at this junction only. Okay. So I selected this node number and select rest forces and moments. Okay. So in forces and moments, how we are going to apply the forces is, one is towards this direction, vertically upwards, and one more is towards this direction, because your flow is in this direction. So always your reaction force will be in opposite direction. This is very important. Vertical also no issue, but horizontal force definitely you have to apply, because your fluid will be moving in this direction only. Okay. So now we are going to apply the reaction force 5715. We'll consider vertical as 5715, and then in the horizontal direction, you see it is in plus x. Okay. So your line is moving in minus x, you have to apply the force in plus x. 5715. Like this you need to apply. Okay. So in the vector one I have applied. Okay. In some cases what we'll do, if two PSVs are there, one is working and one is standby, you will have a bypass. Okay. So in those cases, you need to apply, two forces, F1 and F2. F1 for one working, and F2 for standby, and one more thing is F1 for three forces we need to apply. First, two PSVs are working, then this first one is applicable. Then for the working and standby, if this PSV is working, means you can use vector 2 as you have to apply the force, and this will be your 0. If not working, then you will have no forces. Okay. So vice versa. I will show you in the next this one how to change the temperature for working and standby and all. We will apply the forces here. You see. So here also you have to select this node number and forces and moment. Select. And apply forces in y direction, apply in x direction 5715, and then in the vertical also 5715. Okay, so this arrow is your reaction force. So like this you have to apply. Okay, and one more thing is very important in the PSV lines, the support arrangement. Generally all PSVs know it should have hold down support. Hold down support means like this. It should not allow the pipe to move up and down. Okay. Hold down support at the inlet and axial stop or limit stop at the outlet. Why we have to use like this means, because the reaction forces are there. In order to accommodate the reaction force, we need to design the support accordingly, because your forces will be transferred to the supports only. So you need to design the support based on the reaction force. So you will have more loads in the axial direction. Axial means towards the pipe direction. And here also in the vertical direction you will have more loads. Since we have applied this reaction force in two directions, you have to remember at the inlet hold on support. Hold on support is nothing but, for example, this is a pipe. I will show you in the support class. Shoe is there means okay. So this is a hold on support. I mean this pipe should not move up and down. I have shown some gap, so you have to maintain 0 mm gap so that pipe will not move up and down. Okay, this is a hold on support plus guide. Guide means horizontal direction, this direction. Okay, so pipe will not move vertical up and down and in the horizontal direction. So hold down it should have like that only. Okay. So in this case, since this is a vertical pipe will have we have a hold down arrangement. I will show you that one. And in the outlet, you have to provide limit stop. Limit stop is nothing but axial stop or limit stop something. So this is a shoe. Just I am giving the idea. So the arrangement may be different also. So that depends on your support standard. So for example, this is your pipe. It is, for example, your shoe is resting on the steel. So they will weld this member. So what will happen? This pipe will not move in this direction, axial direction of the pipe. Okay. So this will call it as limit stop. I will show you in detail. We have a lot of pipe support standard. I will show you and I explain you where we need to use. So in PSV you have to remember two things. One is how to apply the reaction forces and what are all the supports to be followed. Main thing is at the inlet means here if you don't have generally if you have spool then you can apply you have to use support here, but here there is no spool, so you can add here. So you change this support to hold down support like this. I will show you. Hold down means in CAESAR how to define y or plus y minus y. 3370 minus y. Okay, like this. This is hold down. And guide 3370. You just give guide, or if you know the direction, if it is Z means Z. So this is guide. This is hold on plus guide support. And if you go to outlet rest support should be there, that is for the shoe, and 3670. Then you can give L means limit stop. If you select this arrow you will have a lot of supports, anchor X, Y, Z, like plus X, minus X, like that. So if limit stop is for axial direction, you see. So it is in axial direction of the pipe. And if you want guide, you can add guide also here. Because if it is on the higher elevation, wind will be there. So definitely we need to add guide. If you give G, guide will be there. Guide means lateral direction of the pipe. Okay. Or if you know the direction correctly, you just give Z. So for limit stop also, if you know exact direction, if X means that limit stop will be act in the X direction. Anything you can give. Okay. But you have to check the stress design basis, because in stress design basis they used to mention for limit stop you have to use LIM only, or you have to use the direction only. If they mention like that, then you have to use the directions only. Otherwise you can use general terms like G for guide, L for limit stop, like that. And here I am just entering L limit stop 4610. This one guide, just I am giving guide. Okay. So here also, so you can give plus y here, or y also you can model. Just y means it will consider plus or minus y, plus and minus y, 4310, and G means guide. Okay. So like this support arrangement is very important for the PSV lines. For example, I mean this hold down and guide depends on the inlet of the pipe. For example, if it is coming from some other equipment, if any equipment is there, if it, okay, so if your line is coming from any equipment, then you should not use hold down and guide here, because your equipment anchor is here. Okay. So equipment, always your movement will be opposite to the anchor point. So this is your anchor point. Okay. So your expansion will be towards upside. So you should not arrest your expansion. What happens means, if you arrest your expansion, then your failure will be at this elbow or at the nozzle. Okay. So you have to use properly the limits of, since here there are only pipes, so I use this hold down support and guide. Okay. So we need to see when once you do the analysis, then you will come to know why we are used. Okay. So this is for the PSV. So once you complete this is the inputs of all the lines, we need to see how to give the buried. How to give the buried. Okay. So generally, so we have completed modeling. What we have to do is save this one, and before that, select the node number, check the node number for the buried portion, 4790. Okay, from here 4790 to 5040. Okay, you have to remember 4790 to 5040. 5040. Okay, just I am okay. Then you close this save and close this window. Okay, close. And then in CAESAR, you have to go in the home, not file, at the home. Underground pipe modeler will be there. See, underground pipe modeler. Select underground pipe modeler. Double click this. Okay. So if you select this buried pipe modeler, underground pipe modeler, your file name has been changed. You see, CALC001-OP. This was your above ground file name. Now -B means B is added. That means this is buried model. So you have to remember. So for the sorry, in any system, if you have above ground as well as buried portion, then you will have two files. One is normal above ground file and buried file. So every time we need to do analysis and we need to convert this normal model into buried model and do the analysis. If you are going to change any supports like that, then you have to update in the above ground model only. Then again you need to convert and then run the analysis. So every time you need to do like this. Okay, so you have to be very careful. Don't change anything on the buried model. So if you if you do analysis, then our data will be lost. So whatever changes you want to make, you do it on the above ground model only. Okay. So now you see, once you select this buried pipe model or underground pipe model, you will get the like Excel sheet. Okay. So generally this user defined lateral K means stiffness values, soil stiff. So this, in some projects they used to enter these values, but generally we will not do like that. We will go to here. You see this soil models. You go to here, you will find this one, soil models. You select this soil model. So in the basic soil modeler, you will have soil model type, model number 2, and soil model type. In soil model type, you have two levels. One is CAESAR basic model and American Lifeline Alliance. So in the stress design basis, it will be defined which one to be used. If you want to use CAESAR basic model, then CAESAR basic model to be used. CAESAR basic model means it will be less, or it will be default value, and your soil density and the buried depth of the pipe and friction angle only you have to enter. No need to enter other values. But if it is an American life science, So in this project they are asked us to use American Life Alliance. Okay. You see, this is a property provided by the client in the design basis. So what we need to, you have to minimize this value. So minimize this window, and also you close this window or minimize this. Because now if any value is wrong, then our entire analysis also will be wrong. Okay. So now you open this soil modeler and you select American Life Science and soil classification. What is your soil classification? You need to see. That will be given in a design basis. For example, if it is sand or gravel, you select gravel, sand or gravel, or clay means you select clay. Okay. So here I think it is sand or gravel only. And F coating factor is 0.6. And GOMO dry soil density, that is 1686. Then GOMO effective soil density is 1686. And then buried depth is 1500. Friction angle CAESAR model number they are not given. So CAESAR model number is 2 only here, we have given already. Okay. And the friction angle is 35 degree. And then K0, coefficient of pressure at rest, 0.384. If they have not provided value, what we need to do is just press F1. You will have some default values. You can use those values also if they are not provided for the initial analysis and all. You can use those values and will be mentioned in the assumption value. Since these values are not provided by the client, so we have used the default CAESAR value. Okay. And DT, it is mentioned as 5. So you go to help, you will get all the details. What is this? What is DT? Yield displacement factor. You see, yield displacement factor axial. So if it is 5 means what is this one? 5 means loose sand. So all these values are for the soil properties, because a pipe will be there, pipe will be covered with the soil. So based on the compactness, your movement will be there. Definitely the axial movement will be there in the buried pipes. So many people thinking that there will not be any movement. Definitely axial moment will be there. So you will see once you complete the analysis. Okay. There will be a huge axial moment. And DP is 0.15. And yield displacement factor upward multiple of H, that is 0.02. And upward multiple of D, yield displacement factor, that is 0.1. And this is also 0.1. And your thermal expansion is 11.7. That is a difference between your operating temperature. Sorry, expansion coefficient you have to take it from 31.3, or yeah, this is 31.3 piping only, no? So 31.3 you need to select based on the material. For A106 grade B, what is the thermal expansion coefficient? You have to take it from 31.3. Okay. And this temperature change, install minus operating. So installation temperature is 21, and that is your ambient temperature, and maximum operating temperature is 82. So if you subtract this value, you will get 61. Okay. Then okay, you have to give OK. So once you enter all the values, you just give OK, and you have to remember model number 2. Okay. So you can add n number of soil, add new soil. Means one more soil, that model number will be 3. Add new soil. model number 4. Like that, you will have different model. See, soil 1 for, that is model number 2. Soil 2, model number 3. Soil 3, model number 4. So this model number you have to enter at the node numbers. So why we are giving this many node number? I mean different models means because in the pipeline, generally for the pipelines this will be used. For cross country pipeline, we have different road crossings, river crossings, canal crossings, and also road crossings at different elevation. Some 1.5 meter will be there, some 2 meters or 3 meters, 5 meters. So different buried depth will be there. So for example, your model number 1, that is soil model 1, model number 2 has 1500 buried depth. And go to the next one, soil model 2, model number 3. So this is 2500. Example I am telling, and go to model number 4. So you may have some 4 meters of buried depth. And also different soil properties also will be there. Might friction angle also will be changed. That depends on the location. Okay. So for that reason, you can add n number of soil models. So now I will delete other 3 models because since this is one line, it is at a very short distance. Because for pipelines up to 100 kilometers also it may run. So it will have different soil properties. Okay, for that purpose only they are given. You need to give like that. So in those cases you have to be very careful where you have to use model number 2, 3, 4. So first you have to note down the node numbers. From which node number to node number your buried depth is 1500. Which node number to node number your buried depth is 3000. Which node number to no other node number your buried depth is 4000. So like that you have to note it down on the book, on the notebook, then only you can enter all the values. So now I am going to delete this soil. Okay, only one model I am going to use. Just once you complete, select OK. Okay, now, so if it is above ground means no need to mention any soil model number. So we know our buried node number 4790 to 5040. So go to 4790, scroll this, or you can pull this one, 4790. You see 4790, this is 4790, this is also 4790, but from 4790 to 4810 only buried portion starts. So what we need to do here, you need to change the soil model number. What we have given here, model number 2. So you have to enter 2 here. And you have to select this from end mesh. So mesh. So it will do the meshing and it will show the soil stiffness value. It will add the soil stiffness value. You see, if you see the note, you will come to know. The buried model of the pipeline system is created by the buried pipe model of CAESAR-2 from the soil parameter input. Whatever you are giving now, that is the soil parameter input. CAESAR-2 automatically calculates the variable soil spring stiffness and ultimate loads and places these at the suitable nodal points of the model. Okay, so whatever node points we are given, that will be there, but CAESAR will do the calculation and it will define its own node numbers. We will see after this. Okay, once you convert the buried model, you will come to know. And in this process, CAESAR-2 overrides a user defined node points. Yeah, already we are given some 2 node numbers only, from and to. But you can see how many node it has been created. We'll see. And provides new model node numbers for the buried sections. Okay. So from here to 4790 to 5040. So this is our end mesh. Because from here to here only buried portion. After that you have to give 0. 0 for above ground portion. Okay. You see this buried model number is 2. That's why we have given 2 for the buried portion. For example, if you have from 4650 to 4750, you have different model. 3 means you can enter like this. You select this one up to here and give 3. We have not defined, but if you define, then it will show like that. I will show. See, I will add this one. So here 2500. Example I'm telling. Okay. From here to here 3. From here to here 3. So you have to tick this one from and end mesh, and after this nothing. Just give 0. Okay. So like this, you have to define the node number properly. Okay. I will delete this one. It's very simple. Okay. Sorry. So once you, I will delete that model. This soil I will delete. Okay. So once you define this one, once you define the buried node numbers, okay, we have defined. Then you here again it's there no soil models. After that, convert is there. Convert normal model to buried model, above ground model into buried model. Okay. So warning is there means okay, just leave it. Okay. So if error is there, you need to correct those error. If you are not properly define the bends, sometimes it will show error. Okay. Then okay. There are warnings means you can leave, it will run. Then select OK. Okay. So if you go, and then what we need to do after conversion, you have to select again piping inputs. So if you go to that particular CAESAR file, this is that CAESAR file. Sorry. This is that CAESAR file. See, your original file is this one, OPE-.c2, and your converted model is this one. Buried model is this file. You see, from this node number onwards, your buried portion starts. Okay, from this node number only we are defined. This is, after this it is 4790 to 4810. What we are given? 4810. 4810, this elbow will have 4810. Okay, you see here. So in between, CAESAR will select and the CAESAR will break the node numbers and provide the soil properties. So these are the stiffness values calculated by CAESAR. So we cannot do anything. Sometimes client used to suggest you just use different stiffness values, means you can change this value. Okay, otherwise no need to change, its default value only we have to use, because based on our soil properties CAESAR has calculated. Okay, you see up to here. So here everywhere a model has been created, converted into buried portion. So see, after this reducer there is not it is not buried, it is normal model only. See, in the reducer there is no stiffness value, so it is normal above ground model. Okay. So like this you need to convert the normal model into above ground model. So in order to get the virtual anchor will be calculated by CAESAR only. That's why for the lengthy lines, so you need to you need to break the lengthier lines into 6 meters in order to get the correct stiffness value. So if it is 29 meter or 30 meter or 50 meters, you need to break into every 9 meters or 6 meters or 10 meters like that. Okay. Okay, tomorrow we'll see the how to include the uh, PSV reaction force in the load cases and how analysis to be done. Okay, thank you very much.